In the last lecture, we let's make it less loud. Yes, it's a complicated device, same complicated as quantum computer. Okay, yes, previous lecture, yes, in particular, we did the following. I introduced several 1-qubit gates and several 2-qubit gates. Yes, and okay, the first half of today's lecture, I would like to continue kind of this topic, and in a very short, it's summarized on this slide. Yes, so actually all unitary 1-qubit gates is possible to implement, and all unitary 2-qubit gates it's possible to implement, given that you can do CNOT operator. Yes, but let us consider a few more details, yes, because we somehow want to write this in the IBM computer, not just, in words and not just on a blackboard. And in that case, there, I don't know, only concrete gates could be implemented. So the question how to create arbitrary gates from those gates which are in computer. And this also gives you some kind of feeling from what could be consistent quantum software development.
Are you going to tell us which are the gates which can generate this history?
So yes, so I'd like to say about this. Yes, I will introduce more gates than the minimal necessary amount, yes, of them. But still, okay, let's just somehow look. Yes, so first I would like to start with 1-qubit gates. Yes, and here I wrote 3 special gates that we call X, Y, and Z gates. And okay, so also unitary gate, yes, but unitary is kind of doing nothing. Yes, and what is special about those gates? First of all, if you look, they are unitary. Yes. The second, if you look, that they are also self-adjoint operators. Yes. So in fact, it's more also correct that actually they are basis for self-adjoint operators. Therefore, so like you can consider all self-adjoint operators as a linear space. Yes, and this would be basis in this space. But it's a motivation how one could create what I later tell. Yes, but in fact, still you could just believe to me that what I'm telling is correct. But because in any case, I'm not going to prove what I'm claiming. Yes, I could claim certain statements unless you don't have concerns why kind of you don't believe me. I would just prefer just to go ahead because like for creating programs, it doesn't matter why it holds if it holds. Yes, and okay, so I have the self-adjoint operators, and in that case, to create from them unitary operators is kind of what I should do is should be exponent I times some real constant times this operator. Yes, by some reason people usually put their divided by 2. Yes, I cannot actually comment why. Yes, but still it becomes a standard. I just following the standard which is there. Yes. So I consider kind of I have I imaginary unit times some real constant times X, the matrix, yes, one of those matrices, and in the end divided by 2. Yes, so why I need to divide by 2, it's not clear, yes, because of course, the family which is generated by alpha divided by 2 and family which is generated by alpha is the same family. Yes, so it's our choice, but people choose that it is divided by 2, and I just follow the standard terminology. Yes, and in that case, okay, I can do this for X, for Y, for Z. Yes, and in that case, okay, I call these rotations, yes. And they are called rotations because if you come back to Bloch sphere, which I introduced for 1 qubit state, they actually act as rotation on a Bloch sphere. Yes, but kind of for us, I don't believe that Bloch sphere is super important, so because of this, I don't pay attention to it. Yes, so for me, this is just 3 gates, and they are usually they are implemented in IBM. Yes, so you can put whatever you want as an alpha, yes, and have this gate round. Yes, and for sure, I mean, if you go to remember this Schrödinger equation business, this means that they are just able to create energy functions which corresponds to these self-adjoint operators. Yes, and the alpha in that case plays role of time. The alpha times Planck constant and so on. So this is 3 rotation gates. And there is, if you do the same with identity matrix, you will get this type of gate. Yes, which, as I told, if it acts just in a single qubit, do nothing, basically. Yes, but it plays essential role. So if we say previous lecture, we considered controlled U operators. Yes, and even that by itself, this operator kind of do nothing. Yes, as a control, this operator, it do already something. Yes, and it is actually would play important role. Yes, quite often we will use it. Yes, so this is 4 gates, and I claim, yes, on the next slide I will show that those 4 gates is enough to create arbitrary one-dimensional, 1 qubit gate. Yes, so if you have those 4 implemented, in fact, 3 is enough of them, then you can implement anything. Yes, and this is how it is done. Yes, it's very simple. Yes, you have to consider Z, Y, Z gate, and in the end to do proper phase shift. But if you carefully see, then all of this has determinant equal to 1. Yes, so you cannot change determinant. Yes, and unitary operator not necessarily have determinant 1, it has determinant with absolute value 1. Yes, so the last one would adjust to it. Yes, and it might be not important if you consider only on this gate, but if you want to include it in the controls, then it becomes important. Yes, and another thing is that if you look, so then Y doesn't have imaginary values there in matrix. Yes, so which means that if you start with no complex numbers in the initial state and only use those gates, so you will stay in real values in coefficients. So in case if you want to go to all possible states, you have to use something either X or Z. Yes, so together with Y. But Y is, of course, the most convenient and the most understandable because this is just a rotation, our classical rotation, yes, on a plane. Yes, so it's easier to imagine it. Yes, and okay, so this, I don't prove this as a theorem. Yes, I ask you to believe me that everything is possible, so you just have 4 parameters, and then you will get arbitrary unitary gate. Yes, and here I show the example how, say, rotation on X, yes, which is not used here, yes, how it can be implemented. Yes, so then, okay, and I ask you to believe to me. Yes, so you just consider rotation of Y and conjugate it with rotation Z. Yes, because of course rotation to angle and rotation to backward angle is inverse to each other, so those matrices are inverse to each other, so this is just conjugate, but okay, they are conjugated. Yes, well, basically that's it with 1 qubit case. Yes? So because so this and that matrix are inverse to each other,
It's a change of variables.
this is change of variables, yes, basically, yes, and the change of variables is by this linear transform, yes. Okay, but all of this I think is not important, I mean, in what we do, yes, so okay, there is important part on change of variables when you try to invent new algorithms, but okay, the course is limited, so we don't touch everything, yes. So still what is claimed here that you can implement any 1-qubit gate and you can restrict yourself by rotation on Y and rotation on Z. Yes, actually, if you want, you can also restrict yourself on rotation of Y and rotation of X. Yes, this is also possible.
You can implement any 1-qubit gate.
Any 1-qubit gate. Yes, any 1-qubit gate. Yes. Okay, so all 1-qubit gates are possible. Let's go to 2-qubit gates. Yes. And okay, here the story is more complex. Yes, so I will not even write, you know, everything down. Yes, but still, so there will be important 2-qubit gate which is controlled U. Yes, where U is some 1-qubit gate. Yes, and this is what we will use in the course a lot for arbitrary U. Yes, for this it's kind of important to know if you can implement it or cannot. Yes, and the answer is yes, you can implement it. Yes, and okay, it's written here. Yes, how to do this? I will kind of this you can check by kind of by straightforward calculations. Yes, but I will omit this because this is really straightforward. Yes. And okay, there is a reason why actually one can create it in such form. So we start with a sum gate. We know the form how it is represented. Yes, U in rotations, and so then we can explicitly write the scheme for controlled U gate. Yes, and let me tell, so that's the only one thing which you need to know, yes, in order to be able to prove this, not by just computing a huge matrix multiplication, yes. This is the following. So if you have the scheme not rotation of whatever, say Y of theta, and after this once again not, yes, this is the same. This is the same, okay, I use this, yes, as rotation with respect to inverse angle. Yes, and if you check this, then after this, you know, it happens that it's easy to prove this without multiplication of the matrices, but only summating the corresponding numbers, yes. And okay, so that's here. I would like also to mention that this is the first time when appears this special gate delta, yes, which is written here. Yes, it is on 0-qubit, on 0 value, on 0 state, it's do nothing. On 1 state, it do phase shift. Yes, so this is phase shift gate basically. Yes, and okay, we know that it could be implementable. In fact, usually it is implemented. So in particular in IBM, it's implemented. Yes, so this is why it is put it like this. What is important to see? So if you have controlled U, then it could be decomposed as a 1-qubit gates and C0 gates. Yes, so I claimed, I think, previous lecture also, but I repeat. So it's necessary to implement only one 2-qubit gate, yes, which is C0. So if your wonderful computer implemented C0, you implement everything. Yes, so this is the exact scheme. Yes, and okay, might be, so if you do controlled U, might be you need 2 C0s. Yes, and okay, multiplication of complexity, of computational complexity by 2 is usually means kind of nothing. Yes, people usually are okay with this. Yes, So kind of in the rest, I would think that all controlled U are possible. Yes, and just will using my schemes control U. Technically, if you consider arbitrary 2-qubit gate, so now, okay, it's not a good idea to put the same letter. Yes, so now if you look at arbitrary 2-qubit gate, it also could be written as a composition of several CNOTs and 1-qubit gates. And this is the minimal known scheme, yes, for arbitrary gate. But come on, I'm not going even to try, yes, to explain why it is working. Because this one is really possible, yes. So this one you can spend good half an hour with this things and really see that, you know, it works, yes. But to this I will not even, you know, spend time. And but yeah, question.
My question is, the second diagram, the one that represents all the operator that runs through all possible qubits, right? So what's the first one?
So no, first one is a good scheme for controlled 1-qubit gate. So if you have a 1-qubit gate, which we know good representation, then you have a representation for controlled U gate. Yes, so here you, kind of, I'm a bad teacher, yes, so I use the same letter for different things, yes.
Okay, so the first one is like the big box, like controlling the other.
Yes. Yes, so let's follow the notation, yes, once again. So this is a string notation, so horizontal line is a qubit, and this notation is controlled U, yes, so which acts the following. If the first qubit is 0, then do nothing. If the first qubit is 1, yes, assume that you're working in basis, yes, so you start with, so you need to check that they works the same in the.
What is controlled by each control? The first control, for instance, between A and B. No, not this one. The first one, yeah.
Here, it's, there is no control. This is just 1-qubit gate applied.
But there is a first control.
Here.
Yeah, yeah.
This is controlled not.
Yeah, what is it controlling?
I mean, this is controlled not operator. It acts on 2 qubits. The first one is controller, and the second one is the controlled qubit. Yes, so how works this guy? Yeah, once again. Yes, so if the first string is 0, then this gate do nothing. If the first string is 1, then the second not is applied. Not operator is applied. Yes? So let's me recall, yes, in this case, yes. So if, yeah.
It just feels like a flip-flop on classical computers.
What means?
It's not a flip-flop. Flip-flop is okay, never mind.
So like I can write this in a very condensed form like this. Might be this would call might be this is flip-flop, yes, operator. But to usually they use control 3-qubit things, 3-bit things in order. It might be, you know, we are slightly confused, yes. But technically you can say that 0, if 0, then second one doesn't change. If x is 1, then the second one is changed. Yes? Are you convinced? Or mais ou menos? No, are you? Yeah? So this is how the scheme could be, yes? So because we will use controlled U a lot, and actually the IBM allows you to do controlled U for any U, yes, in the end. So this is what is inside, yes, because there is a clear way, constructive way how to do this, so they do this. And the same actually this way is also constructive. Yes, but okay, not so easy because how to say, you need to represent you need to represent 2-qubit gate somehow, and of course this is much more parameters. Yes, for its 6 plus 4, 10 parameters. Yes, so this is 10 parameter family. I mean, I would not try to write expressions like this. Yes, because for yeah. So there, okay, so we will have some, demonstration how it works once again, yes, in more details, yes. By the way, I encourage everybody to register in IBM Quantum Computing, yes, so, and please reply in the Telegram chat if you are there to have you did this, so I understand what is the true state of the audience. So kind of, okay, you cannot say any U. Yes, you are able there to write control, you are able to put there those operators. Yes, and then in the end you will create any of them. Yes, but, and of course what is true, if you have that U is equal to what, okay, I will write A, B, yes, if it is correct, yes, if it is true, then actually controlled U, yes, is equivalent to controlled A, yes, and controlled B. Yes, so this is the lazy way. Yes, so to any operator which you can put in IBM to string, yes, then you can able to do controlled this operator, yes, as well. Yes, and okay, the lazy form of implementation is like this, yes, but this is lazy form. Yes, it's possible to have more efficient form. Yes, and in this case, in the cases when IBM can do this, it does this, yes. But here, if I do everything if I do everything. Yes, I can do everything with lazy way. Yeah, it's possible to do everything with lazy way. Yes, so it's question of optimization. Yes, you see, because okay, if I follow lazy construction, that for any U, I will put 4 gates, and I put control on each of them, and each of them will be opened as a stuff like this. So it will be 8 CNOT operators. Yes, but it was possible to do it with 3. Yes, kind of. This is and 3 and 8. How to say? Like technically, from complexity, computational complexity point of view, they leave you in the same class. Yes, but we are far from the. Yes. Yeah. Yeah, it uses 3 other operators. Yes. Yeah.
I can write use this operator in IBM computer, and they will calculate.
Let us see. So I have a possibility, so we have a nice thing, and in each lecture I would like to spend some time really in IBM computer, yes, so this would be, let me show, this is a good question, and let me show how it's done. Yes, so I take new file, yes, so that's, so and you will learn as well how to do control. So I put Adamar operator, yes, which we know how to do, yes. And now I create control Adamar, yes, and this I can do by the following. So I take this point, yes, which means control. Yes, and by the way, I send not only lecture notes, but some PDF file, yes, as well, which I call the Gates exercises, something like this. And there, it is created in such a form that it's shown actually how to run all the basic gates there. Yes, and in particular, I can put dot, yes, which is controlled, and I can do the following. I just drag and drop it into H. It suggests me to choose. With which qubit it's controlled. So let me choose this one, and now I have control Adamar. Yes, and we can actually go there and see edit gate, and we see what actually it is doing. Yes, on the right hand side, on a real computer. Yes, so it did this decomposition by itself. Yes, so and technically it follows exactly what I told. Yes, so there is two CNOT operators. Yes, and this is proper. Might be this is a proper rotations, but and so on. Yes, might be this is a proper way of such decomposition. So with here, because there is some H as well, and we know that H he will actually decompose even more. Yes, in the end. Yes, but there is this some S inverse T operator. Yes, so it has some basic operators which I implement. He creates by himself, so he not necessarily follows exactly the thing which I told. Yes, but still it's possible. Yes, and you see that actually the fact that this is two control nodes stays like this. Yes, so it's cannot do this with one. Yes, so does it answers to your? You see, yes, so actually the feature is that, the feature or a problem, you cannot write any U. Yes, you have to specify it in terms of operators which are here, basically, yes. You can choose, say, where is rotation of Y. Yes, you can choose rotation of Y, yes, and you can say on which angle it is rotation. Let me be P over 6, yes. And you go here, you can put controlled once again, yes, and do something. Yes, and it's, you do control, yes, and it shows you how it will be implemented. Yes, and here there is, it's called U3, yes, and it's actually arbitrary gate. Yes, you can, there is really thing for arbitrary gate, yes, here. Yes, but if you look, so there are 3 parameters, and they're not exactly the same parameters as I showed. Yes, so this is. Yes, so this is always the case, because you are referring to a concrete device. Yes, then you have to end up with the things which this device is implementing. Yes, what I told here is only the following: any unitary gate you are able to implement. Yes, which is not bad. Yes. So let me go back to presentation. Yes. So this is the idea how any 2-qubit gates can be implemented. Yes. And now, let me mention several special 2-qubit gates, which are usually somehow, quite often, somehow implemented on the device. And the reason, there are several reasons for this. First of all, swap. It just changes 2 qubits, how exchange 2 qubits by their positions. Yes, it's it's very important gate. And the next slide I show why. Yes, but it actually doesn't serve as a completely important 2-qubit gate. It's not enough, because if the state was direct product, then after swap operator, it is still direct product. Yeah, so you cannot create these entangled states. Yeah, so you cannot get profit. Yes, so swap is important, but it cannot be the only 2-qubit gate which is implemented. There are another 2 gates, CSINE and ISWAP. Yes, so their matrices is written here, and I put it on the slide because in some computers, instead of CNOT, implemented one of those 2 gates. Yes, and it's possible actually if you have implementation of this one or that one, it's possible to create any 2-qubit gates as well. But let me not show the similar schemes as on previous slide. Yes, because there is no reason. Yes, and okay, swap technically can be represented as a CNOT gates, but this is, you see, CNOT makes a lot of entanglement. Yes, and kind of in the end you have 0 entanglement. Yes, so which tells you that actually it's not possible always to increase. Yes, so there is entanglement. It's possible to get from state which is not direct product, a state which is direct product. Yes, and this is the notation. Yes, and I will several times do, because you have to get used to it. Yes, to this notation. Why swap operator is super important. And the problem is, okay, it's a strange slide, yes. The problem is that in the physical devices, at least in IBM, but actually in all known to me physical devices, yes, you cannot say you can apply 1-qubit gate to any qubit. This is possible. But you cannot apply CNOT gate, so 2-qubit gate, to arbitrary 2 qubits. You can apply only to neighbor qubits. Yes, because, okay, this is the limitation of physics. And it seems that this such type of limitation always will exist, yes, in the end. And so there is some connectivity graph. So which qubits are connected, which are neighbors and which are not neighbors, yes? So, and so we will run always on 5-qubit gates, because this is the only free available, yes? And 5-qubit computers, yes? And so there are 2 possible graphs, either they're in a straight line, yes, or they are in T construction, yes? And if you work with the biggest one, 127, I think, I might be mistaken by 1 or 2 qubits, yes, 127, then you have a certain strange graph. Yes, and then, okay, it becomes not convenient, because you have to think always to which you can run CNOT, on which you cannot run CNOT. And the answer is no, you don't need to think this very much, yes, because you choose any 2 and you want to run CNOT gate, and assume that your computer is perfect, then you can do swaps between neighbors, yes, make them connected, make their neighbors, do CNOT and do swap back. Yes, okay, if you want to do 0 and, this one, 113, then number of swaps will be quite a lot, yes. But technically, it's possible, yes. Yeah? Errors.
It seems to me like it adds a little bit of efficiency
Yes. Answer is yes. It creates a lot of not efficiency, yes, because as I mentioned, first of all, each operator has certain unperfectness, yes, it's not perfect, so you get some error, yes, and you will, even if they're just summating, yes, so then you have a lot. Another point of view, if you look on a complexity class, so how, like in terms of n, yes, it works. And so if you compare exponential and polynomial, yes, it doesn't change this type of class because you can replace any operation with no more than n times, no more than n operations. Yes, so it doesn't change between polynomial and exponential. But inside, say, polynomial class, it can move you from quadratic to cubic. Yeah, so that's a pity, yes. But since, future is not clear up to now, yes, of quantum computers. What would be the end? Would they have huge thing with certain graphs, or they will create a full graph in the end? Yes, it's not clear. From what I see, they will try to put more and more connection. What?
I mean, even the system that says, okay, so I have to index this gate to that gate and know that, okay, in this part of the program I should swap. Is it in the hands of the programmer which bit will be where, or?
No, technically it's in hand of the programmer because you put all your gates on things with numbers. Yes, of course, there is certain compiler inside, but it's actually the same happening with assembler, yes? So kind of you write on C++, it's translated to assembler, yes, there it could be some optimizations or de-optimizations, yes? And after this, you translate assembler to machine codes, yes? And in the end, you also cannot apply logical operator to any, yes, to I don't know, things in processor. Yes, you still also has some restrictions, but there is some engine which works for you. Yes, and here is the same. Actually, when you run your program on computer, sometimes compiler, yes, reordering qubits exactly in order to have better construction here. Yes, so this is so they thinking about this, yes. But this swap operator is important just because we can forget, yes, having might be n as a multiplier for time of work. And this is what I would do in the rest of the course, yes, because kind of it's, you see, because it depends on the graph. Now it's too early to build this theory because we don't know how this graph will look like, yes, in the end. Because even there is a huge difference between this one and that one, yes. One is acyclic and another is with cycles, yes. And is it necessary that this is planar graph? This depends on physics, which we don't touch here up to now, yes. And it's too early. So when we will have a first real processor, let's. Okay, we have first real processor, but we are not actually doing this. And in order to show, the difference, yes. So this is permutation. Yes, I want just to reorder qubits, yes, to make them inverse, inverse order. Very easy task, yes. And if I would like to do it in my paradigm, yes, so when I can apply any operators, any two qubit operators to any two qubits, then it's easy, yes, to be done. Yes, and the complexity is n divided by 2. Yes, for odd, even, let me not show the details. Yes, but if I'm allowed to do only with neighbors, which is the case, in fact, this is the optimal schemes which you can have. Yes, I believe it is proved that they are optimal, but I don't, yeah. So like for even you would do like this, you can check, that it is actually the same. That kind of it see that this one, okay, will goes to here, after this to here, after this to here. Yes, and now you should trace the path of any of them, yes, and to recognize that, yes, really they're doing this. Yes, but here the complexity is proportional to n squared. Yes, so you really lose this 1 power of complexity because you have to do only for neighbors. Yes, this of course refers not to arbitrary, not to, this refers to, graphs like this, yes, not like this, yes, but I mean, I don't know actually the problem of reordering with neighbors here. I think it's a good combinatorial problem, yes, as for those who enjoy combinatorics. And okay, yes, this is permutation. So now actually the lecture will consist most of the examples of, so I would impose a problem, yes, and I would solve it for you here, yes. And if you have time in the end of the lecture, I have finite number of problems. We will spend time with the IBM computer, yes, and you know, implement might be one of them and really run. Yes, so important thing, one of you, I don't remember who, asked the question, can we measure and depending on the result continue our scheme in one way or other? Yes, and I answered that yes, technically you can, but people not really practice this. Yes, and here is the reason. And the reason is the following. So assume that you do some, you know, scheme. After this you measure, yes, and depending on the result of measurement, you do something with other qubits. Yes, or not do. Yeah, do or not do. Then it happens that it gives you the same result as you just put controlled V operator and do measurement. Yes, and okay, it's easier to calculate that the probability of 0 and 1 on this would be the same. Yes, and okay, you need to spend a bit more time because here when you do measurement, you also do some projection there. Yes, so there is some job to be done. But if you carefully check, you will realize that actually if you get 0, then the final state here and here will be the same. If you get here 1, the final state here on the left, on the right scheme would be the same, just straightforward calculation. So I omit it. Yes, so from one point of view, it tells that, okay, it's not necessary to use such type of things, yes. But from another point of view, it's there is another point of view, because this is controlled V, and each controlled operator is pain, yes, gives you some errors. Yes, so it's a good idea to have as less control operators as possible, and this trick potentially allows you to have less. Yes, but you see, there is not possibility to get gain more than n, like the qubits, n, not more than proportional to n, basically. Yes, so that's not a big story. Yes, no, you cannot get a lot of gain in it. Okay, later I show why what I told is not correct. So how the situations when it can create more gain, but yeah.
I have a question. Does the number of total measurements would be the same in both diagrams?
Yes, because here there is one measurement, here there is one measurement. Yes, and the
I'll change the question. Like, if connected to V, there would be another measurement.
okay.
Now,
A controlled measurement, yes. No, okay, then of course I speak that V here is unitary operator, yes. So if you have here scheme which is with measurement, if there is a scheme with measurement, controlled measurement, yes, we haven't looked into this. Yeah, I think control measurement is not a unitary gate, so you cannot implement it basically, yes. So until measurement, it could be the same, But after you want to do another measurement, yes, you already go outside of the unitary operators class, you already have to do measurement. So at that time, you kind of insisted. If you want to do control measurement, you have to measure. Yes, hypothesis.
Would be that the number of measurements of the first scheme would be like the multiplication of the picture. I don't know, because I'm just wondering, because each measurement would impact a state on the other gate.
It would, on the other qubits, it has impact on other qubits, potentially, yeah.
And the state of the, it's just a hypothesis, maybe it's wrong, I don't know. And then but for each measurement, I would need to make another measurement on the second, the gate would be.
No, but you remember that you need to do, basically you can do only one measurement, because if you measure what is measured, you will get the same result.
Also, the D state, the second gate would be already collapsed.
Yeah, so kind of if I do measurement here, yes, and after this whatever I do with other gates here, if I do second time measurement of a first one, it would always give the, so the first time it's probabilistic, yes, with some probability 0, with some probability 1, but after you measure it, it will give you the same result, unless you start to put here new other gates, yes, which is actually now possible on quantum computers, but this is a new story. Yes, so like before, in the beginning, yes, it was not possible. So after you measure something, so you lose this qubit, yes, but now it's possible.
You should not wait too much to make the second measurement. Be sure that the measurement
Once again, we speak about ideal quantum computer, yes, so this is kind of a course about ideal quantum computer, which doesn't.
ideal even those don't exist yet.
Yeah. Okay, so at some point I should make a break. I think this is a good time to make a break. Okay, let's continue. Yeah. So, controlled operators are very important. Yes, so they would a basic block actually of most of the algorithms. So I would like, to play a bit more, yes, with this and to show variations of it which exist. Yes, so first of all, it could be controlled not by 1, but it could be controlled by 0. So if 0, we do something. If 1, we don't do something. If we don't do anything. Yes, and in that case, it's denoted like this. Yes, it's the same, but dot now is not black. It's, how to say, empty. Yes, empty circle. And okay, it doesn't actually. It could be very easily to implement it in with gates which we already have seen. So if you just do not, after this do control Q and not once again, then you will get controlled by 0. Yes, and actually because it doesn't change number of controls, I would just always use like this and never pay attention actually on how it works. So another thing is more hard, which I would like to say, is that I can do control not only for 1 qubit gates, yes, technically, but for multi-qubit gates, yes. Then it becomes, if it was operator on n gates, this becomes operator on n plus 1 gates. It's still possible to implement in using just CNOTs and 1 qubit gates, but now it becomes more challenging. Yes, we will see next slides what one can do about this. Yes, but I will use this as a logical paradigm. Yes, so sometimes I would refer to such a gate, yes, without kind of going into details how to implement it. Okay, we know how to implement it. Yes, I will teach next slide how to do this. Yes, yes, Charles.
Sometimes you say technically. What do you mean by that?
What means?
I don't know. You say that.
Well, can you repeat the full phrase, please?
You make sentences that technically you can do that.
Yeah, okay, this I mean that if you go, so here there are two differences. Yes, so if I write for ideal world, yes, when I can do everything with perfect computer, then it actually has no difference. Yes, this is what I mean, technically you can do. Because when you really try to do this, you encounter with the fact that, okay, there is a huge difference between different implementations, yes, but by the quality of how it is done, yes. And I don't touch how exactly, but of course, there are a lot of papers which studies which implementation is better, yes, and how to do better implementations, and what means better, yes, because it's also not clear. Yes, so I introduced controlled of multi-dimension, of multi-gate. Yes, and of course you can just by induction now implement and of controlled gate. Yes, because, okay, so assume that you know how to do controlled U, and we know, and this is a two-dimensional, two qubit gate, so we can do controlled 2 qubit gate, and this becomes controlled. And okay, now it's 3 qubit gate, and you can add 1 more control, and so on. Yeah, so this is definition by induction. Yes, and I use this as a logic paradigm, and I will spend quite a lot time of this lecture to speak about how to implement such kind of things. It's not trivial. Yes, so it's not trivial how to reduce it to CNOTs and so on. So first of all, there is a easier way. So there is a equality. So you have controlled U, and you consider V as a square root of U operation. Then the following equality holds. Yeah, so basically you can decompose it into several control V and CNOTs. Yes, and this is how it is done. Yes, it's easy to see because, okay, the first never changes because, nothing changes it. The second qubit, so there are two possibilities. Either this works or not works. Yes, but it's do this either 0 time or 2 times. Yes, and not, so in the end, this qubit doesn't change. I'm speaking, assuming that I work in basis. Yes, so I work in some pure state. Yes, and if this equality holds for any pure state, then it holds for all linear space. Yes, and okay, now let us see what is happening if, say, both of them are equal to 1. What's happening with the third one? So, first of all, we apply V. Second, we apply C naught, and this becomes 0 now. So we do not apply V inverse. Yes, so this notation is for inverse. Yes. What? This notation is V inverse. Yes. And okay, the last one you do. Yes, so it's V squared, so this is U. And if, okay, if both of them are 0, yes, then you apply nothing. Yes, if one of them 0, one of them is 1, then actually it will happen that you apply 1 V and 1 V minus 1, so in the end you get identity. So, and okay, using this paradigm, yes, you of course can implement control as many as you want. Yes, because here I actually never use the fact that this is a 1 qubit. Yes, it could be any number of qubits. Yes, but here there is a tiny detail, yes, which actually makes this not so powerful. Because now if I look, because now each controlled U becomes 3 control V. And each time I go deeper, yes, consider more control nodes, yes, I multiply number of control operators which I have. So if I would like to have n depth, so control n times, then I would have exponential number of control V in the end. And so I lost all the beauty, all the powerful of quantum computer, yes, because I decided to go from polynomial class to exponential class immediately. So this is why, you should be careful. So this tells that yes, you can, I would not use the word technically, not to confuse you, yes, so you can use this paradigm in order to implement it, yes, but in that case you just lose a lot. So you have to be careful and try to create other possibilities if you can. Yes, and sometimes later I show that sometimes you can. Actually, if you would like to refer to this for arbitrary operator U, then okay, there is a way to do this better than by just this scheme, but still exponential.
I will refer again classical because it reminds me of how we design some gates, and there's like a algebra called Boolean algebra that
Okay.
we use. And my question is, how it's called the algebra, this algebra that describes like, because I don't know, like if there is a way to describe this with some kind of algebra operators, maybe it's a way to find simplifications. I'm interested. It's a scientific question because I'm interested in okay, so how can I?
So I don't know name. I don't know name, yes, but the true story is when you work with quantum computers, now you don't have a combinatorial type of space, yes, which is 0, 1, and how they go to each other. You switch to linear space, yes, and to linear operators in linear spaces. Yes, so this is a significant difference. For instance, you can consider U as a NOT operator, which still acts from 0 and 1 and preserve your. So C not exist in Boolean algebra. But then I go to V, which is square root of not, which do not exist in Boolean algebra anymore. And I show how to implement it with this. Yes? So, okay, the true answer that I don't know answer to your question. Yes.
I'm not claiming that Boolean would solve it. I'm just
Yeah. So no, but no, this is algebra of the unitary operators in tensor product space. I don't know. Charles might be knows the name better than me.
I have a question. I'll bring up. Everything is linear until you have measurements.
Yes.
Measurements, you lose linearity.
So you see, kind of looking onto this slide, I showed that basically you are allowed to put all the measurements in the end. Yes, so you do some unitary operator, and after this, you in the end do measurements. So this is how it could work. Yes, any program. If we forget about this, if we stop to count exactly how many was C nodes, like control operators, and distinguish it with normal operator, with just one qubit operators. Unless we do this, it becomes not important that you can do measurements in the middle.
Yeah, but it was good. I mean,
Okay, yeah. So I kind of ignore this question up to now. Yes, because in fact I also ignore that I'm allow myself to write controlled U operator with any two qubits. Yes, while there is a swap operators inside, and actually I have to take carefully into consideration the graph and optimize because of this strange structure. Yes, so I should do this, and I don't do this. Yes, because not everything is known, understand, and I think there are papers which are doing this. Okay, concerning graph, I don't know. Definitely there are papers which works how it is better to construct the scheme so it would be more stable to quantum errors. Yes, so this is. Yes, okay. So let me see. For one special case, for controlled not, I would like to, this is a very well developed story, how to implement them. Yes, and here appears a nice paradigma that you can use ancilla qubits, so some external qubit, which just helps you to do what you want to do, but not affecting the result at all. So assume for a second that you have this ancilla qubit in a state 0 and not entangled to anything. Yes, and let me consider the half of the scheme. Yes, half of this one. Yes, so then what is happening when it would run? Yes, only if you flip it, this ancilla qubit. Yes, and so those was 1, and if you flip it, so those should be 1. Yes. What? I add just one qubit to my scheme. So I want to implement this controlled not.
and then see that when you say
When I say ancilla qubit, it's just extra qubit. I mean, this doesn't have any meaning. Ancilla is a word from a human sense, not from mathematics sense. Yes, so there is no definition of ancilla. It's just extra qubit. Let me assume that I have an extra qubit which helps to my work. Yes. Yeah. Yes. So this is kind of, if it was 0, then the first two things would help me. But this I have to assume that it was 0. So this means that I cannot use this qubit in any other calculations, which is too expensive, yes, usually. But in that case, there is a trick which is called uncalculating, yes. So I kind of repeat the same scheme second time. Yes, so I repeated it. And now it happens that actually it's not important what was the state of this bit. Yes, on computing, yes, it's called. It's not important what it is. Was it 0 or 1? And in the end, it also will be the same. Yes, and the reason that, okay, if it was 1, okay, this time and all of them was, say, all of those guys were 1, yes, then this one flipped. Yes, then this doesn't work, but this one flips again. Yes, and so this works. So we applied it. Yes, and what happened with this one? It was started as a 1. Yes, and it flipped 2 times, so it is still 1. So, and I just showed this as an example, but actually it's like true for any state. Yes, so this is really equivalent to this one, and this qubit doesn't change. Yes, kind of. It's really equivalent as a schemes. Yes, so
What is the statement?
the statement that this scheme is equivalent to this one.
So that's true only for this. That's not more general than that. I mean, for any number of
For any number of those qubits and any separation of this set into 2 other sets, 2 subsets, it's true. Yes, and basically now I use this scheme, which, okay, we observed and kind of proved. Yes, that true proof I leave as an exercise. So now if we consider L of n, then minimal number of gates which we need to implement C not, yes, then what is written here is written here that if we want to consider n plus k, yes, then it is enough to put 2 times n C naught and 2 times k plus 1 C naught. Yeah, so we have this inequality. Yes, which you can work a bit and prove that it actually means that L of n is proportional to n squared. Yes, and squared because you have 2 here. Yes, basically. And but okay, I leave this how you deduce this. Those who studied complexity theory did this exercise 10 times. Yes, those who didn't study complexity theory, please just trust me. Yes. So this is the thing. So what is the statement? So previous time I didn't use any ancilla qubit. So I didn't use extra qubits, and it was exponential time. Now I used 1 ancilla qubit, and my time becomes quadratic. It's a huge speed up. Okay, so there is somewhere where, we as a mathematicians can, enter the game. Yes, and okay, actually, okay, I put it here like this, and with not many comments, in fact, yes. So if we can use a lot, yes, actually, so if it was C naught with n C, we are able to use n minus 2 ancilla qubits, yes, then there is a scheme which linearly log, yes, so here I did reduce everything to controlled not, yes, but okay, control not can be decomposed into some scheme of finite size, yes, so we will multiply on something, but on a constant number also, so it leaves us still linear, yes, and this is linear scheme, and it, okay, I would not comment it a lot, yes, okay? Okay.
Because the second diagram is huge and it takes a lot of components and each component has its error and stuff like that. Like, why?
Now, the problem is that, okay, if you look on the left thing, yes, so there is no such gate. Yes, so there is no such implementation in a physical device. The physical device, you always limit it to, say, C naught and 1-dimensional, 1-qubit gates. So you have As a software developer, you write, let me do CC not. Yes, but in the end, inside it's somehow decomposed.
In what sense? Because there is nothing, there is no quantum computer.
Yeah.
So nothing exists.
Yes.
In what sense does that even less exist in a now you say these gates do not exist in the computer, but nothing exists in the computer. So what is the meaning when you say,
So, in the beginning, I imposed the paradigm, yes, which tells that I assume that only small qubit gates are possible on a physical device. Yes, so where small is
are you sure?
2 or 3. Okay, in current implementations, it is true.
Yeah, but it's not implementation of actual.
I mean, Charles, yes, we speak about an imaginary device, and you tell, let us speak about another imaginary device.
That's what you do, not me. You say this is not possible, but those are not possible.
So I use, so let me stay in the course as I teach it, yes, in the paradigm which I teach. So I assume that only 1 and 2 qubit operations are possible, yes, and the rest we need to create by ourselves, yes, how we do this, yes. And here, yes, this control not doesn't exist as a basic element of my computer, so I have to create a decomposition. And this is intermediate step to create this decomposition. Yes, and after this, okay, I also need to show how to do controlled not, how to decompose it in 1 and 2 qubit gates, but this I already showed for arbitrary CCU, yes. So, but actually, there are, for controlled not, there are other implementations, but I don't want, to go too deep to this detail. Yes, so this is what is possible, yes, and so this answers to the following question, which we never actually pay attention when we do with classical computers. Because when we work with classical memory, we usually think that we have as much extra memory as we want. Yes, or at least, okay, we need just to double it, let's double it. Yes? Yes, but here, yes, we are in quantum computers. Yes, so it is really the story that each qubit is like a gold yes, thing, because idea that let us double number of qubits, it's like forget about this. It's a huge complexity increasing of complexity. Yes, so, and okay, let me consider so we played a bit with CC not, let me consider as a toy problem, yes, so how to implement the following permutation, a different permutation, which means that, okay, if we are in a state K, we go to state K plus 1, modulus 2 to the power n. Yes, so plus 1. And okay, so if you allow yourself multiple controls and if you allow permutation which I already used, and this looks as a nice expression like this. Yes, and basically I just reordered because it's more convenient because we usually write control up and controlled down. This is just for this case. But here, okay, when you need to flip the first one, only if all the previous are ones. Yeah, so then you flip it. So when you need to flip a second one, only of everything which is beyond it are 1. Yeah, so this is key. Yes, and so in order to implement plus 1, you just need multiple control not. Yes, and okay, how to say, technically we learned. Yes, so no, not technically we learned how to implement them. Yes, and so we can look how different is implementation of them depending on how many ancilla qubits we would like to use. Yes, here it is written for 4 qubits, yes, case when we don't use any ancilla qubit. And I allow myself also to use controlled not, because actually it has special implementations. So okay, and in IBM you're allowed just to put it here, and it take care by itself how to do with this. Yes, and this is the scheme how it will work. Yes, because Rx is a kind of square root of square root of square root of square root of naught. Yes, Rx with certain parameter. Yes, there. And okay, this is how the scheme looks like. Yes, if you just implement it. First nodes are just to set up all one. Yes, and this is how it actual decomposition looks like on a true computer. And I don't want actually to spend a long time investigating it, just to show the scroll size. Yes. Which means that this is approximately 1/5 of the scheme. Yeah, so it's quite long. Yes, now I use 1 ancilla qubit. Yes, and the original scheme, you even can read it. Yes, which is much better. Okay, actually the scheme is still long. Yes, because you see this is 1/4 of the scheme. And now, okay, if you want to use a lot of ancilla qubits, then you can also do like +1 the same way as we were teaching high school. Yes, so that's +1 and to memory, to memory, to memory. So then you need to do some action, and you see here it becomes scheme like this. Okay, I didn't put it actually here how it's decomposed, but you see it. Okay, I didn't put how it is decomposed because it uses 7 qubits, and 7 is, okay, I'm not able to run on a true computer. Yes. Okay, that's it with +1. Yes. The next topic would be how to record numbers inside quantum computer with not very efficient algorithm, but it works nice for few qubits. Yes, and you know, because I want you to be able to practice. Yes, so this is a good idea to have. But now might be you want to ask something about this +1 story. No, okay, good, because actually the way how we would write numbers inside computer follows the same ideas as +1. There's a lot of similarity will be there. And okay, what is the goal? Yes, what means to write something? So I just have sequence of numbers, x0, x1, x2, okay, from 1 to n. Yes, okay, not from 0, from 1 to n. And I just want to, okay, I better write 0. I'm sorry, and n minus 1 there, yes. Then I want to create such a state. Yes, this is my goal. Yes, so this is just what the algorithm for doing this I am proposing. Yes, and of course you have no chances to do this less than with capital N operations. Yes, because you have capital N numbers to be encoded. Yes, so not less than this number. Unfortunately, the algorithm which I propose will use more. Sorry for this. Yes, and okay. First of all, I do something. So let me first assume that they are all positive. Yes, so that they are real and positive. The most general form of the problem is that there are any complex numbers. Yes, but let me first do this for real numbers, and only in the end show what is tiny detail which allows it to, which you need to change if you want to have sign and you have to have complex numbers there. So first of all, I construct such a tree, yes, binary tree. So I write down here all elements which I have, and the neighbor, so not neighbor, but first and second, third and fourth, elements, I consider the couple and I consider their squares and summate them. After this, I have here squares and summate them, and so on. I have a binary tree. Yes, and in the upstairs, I have sum of squares, and let me, for simplicity, assume that it was 1. Yes, because in another case, I need just to divide them to normalize them. Let me assume that the sum of the squares was 1. And okay, now I have here written numbers. Yes, so I constructed this tree. Now I show the scheme how it should be. So I start with 0, 0 state. Yes, and let me see. So I will draw on a blackboard the way how I construct the scheme, just because I want to have it gate by gate appear. It's very hard for video recording because I will refer to both, but okay. So I have this logarithm of m gates. And what I'm going to do, I will decompose my algorithm into several steps. And on each step, I would go just for one of the levels, yes, of this tree, and create on, say, on stage 3, I would create something on 2 qubits corresponding to these numbers. Yes, so this is what I would do. And so I start with all zeros, which corresponds that, okay, I started with everything is sum of is equal to 1. And now I would like to put on the first qubit the situation that coefficient here is square root of what is written here. Coefficient in front of 0 is square root of what is written here, and coefficient in front of 1 is square root of what is written here. And okay, I wrote this. For this, I need to calculate such a ratio of this value to this. Take square root and take cosinus. Yes, why are cosinus? Trust me. Yes, and okay, I got some number theta. And now to the first qubit, I apply gate, which moves 0 to the state cosinus theta 0 plus sinus theta 1. Such gate exists. It's actually Ry in terms with a proper angle, in terms which we discussed before. So I start with some Ry. So I now in this line. Now I would like make on 2 qubits state which corresponding to these 4 numbers. Yes, I looked on the left side. Okay, this is 0, yes, which corresponds to 0 as a first qubit. And I want to decompose it to 0, 0 and 0, 1 with the proper coefficients. And I do once again, I consider this number, divide by this number, make square root of it, take our cosinus. But now I need to run this thing only if the first qubit is equal to 0. So only for this branch. Yes? And so I write this Ry. Yes, and I repeat a similar story for the right branch. Yes, and I write here, so controlled now by 1 of another Ry. Yes, and if I go deeper, deeper, and deeper, then it would appear as an algorithm. Yes, so 0, 0, Ry, 0, 1, Ry, 1, 0, Ry, and 1, 1, Ry. Yes, so this would be. And so on. Yes, deeper I go, more steps on each level I have. Yes, and it good. If you carefully calculate number of gates which are written here, then it would be 2 times capital N. Yes, then because number of them exponentially growing, yes, so this 1, 2, 4, yes, and then the end is 2 to the power number of qubits, yes, which is 2 times 2 to the power qubits minus 1, yes, so basically to N. And this would be a nice algorithm, yes, if you can do, so if you can write down N values with 2N operations, this is perfect. Yes, I mean, you don't lose in complexity anything. But there is a problem, yes, that I do controlled, 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 controlled. Yes, and we know that to implement controlled, controlled, control is not an easy story. Yes, so kind of potentially, if you just don't do this carefully, then you have n squared. So in order to put n numbers, you need n squared time. Yes, which is good or not good, it's questionable, yes, because, okay, you should not assume that you unload the data, which is the maximal capacity of quantum computer, because in that case, it's already kind of exponential time, and you cannot go beyond the exponential class. Yes, so you should, how to say, consider smaller number of qubits to upload, yes, so might be, you know, it works okay. But, okay, this is the way how one can upload this. And, yes, okay, yeah, science, yes, how to encode the proper sign, yes. So after this, after you do everything, and now you have all the numbers as a coefficient, you want to do some sign. Yes, then depending on what was the sign of the last thing, you just also can apply one of the controlled qubits, and actually you can do the same with complex numbers. But I don't go into details because, I mean, it's already too much, yes. And this is the way how you can encode upload numbers into quantum computer. Yes, so okay, that's it with theory. Yes, I also prepared some small document with kind of small instruction of how you can use quantum computer, and some exercises for you to check. Yes, and from now on, each lecture I would start with a short. So now the 2 lectures left, but the last 2 lectures, I would start with your questions, how to implement something. Yes, because I'm sure that if one of you have questions, that it means that at least you tried and you were not successful. So a lot of people would learn something from my answer to this question. Okay, this would not be a long section because I would like to keep going. Yes, but each time I start with this, and let me show you the file, how it is, how one can read it. Yes. Okay, it seems that unfortunately we do not have time to actual demonstration. Yes, but yes, so the file. Yes, so how it's look. So first of all, I show here 2 links where actually by IBM everything is written, might be even better than I do. Yes, but my experience shows that by some reasons material which I show people, which I send people read more frequent than just web links in IBM, even that they are better because, you know, they spend a lot of time, you know, they cover everything and so on. Yes, so there is one thing. So if one would like to see explanation of all gates, there is a thing. So you go here, say, to this information, yes, and you can say open glossary, and wait a bit while internet is working. Yes, it shows all the gates which are there with the explanation of what is done there and so on. Yes. Here I showed in my file certain standardized explanation of what is doing in the notation of the course, basically. So say Adamar gate, I show the matrix, first 2 by 2 matrix which correspond to it, and actions on state 0 and state 1. Yes, and I do this for Adamar, for NOT, for Y, for Z, for special S gate, which we didn't consider, but it might be important for you. Yes, and so on. Then phase gate, so which appeared, but only once appeared. Yes, so it is implemented by IBM, so you can just put it on the diagram. Yes. So I show how one can edit those gates, set up parameters and so on. Yes, so just I scroll this. Yes, and yes, and I would like special measurement also. We touched this previous time, and there is a special gate to set up 0. This is because it's not clear how it works. Yes, so let me tell how it actually works. So if you put this state into your scheme, so yes, what it is doing, it's actually equivalent to the following. So it makes a measurement. Yes, on the K you kind of lose the result of measurement, but measurement is made. And after this you set up at 0. So at that moment you not really know the state of other part of computer, because there was a measurement, there was something probabilistic there. But still it is good, because in fact it is better in quality of implementation. So this thing works better rather than you physically measure, get the result, and independently put 0. I don't know why. It is physics. It's outside of my competence. Yes, but they are doing this, and they claim that it really sometimes works better. So, what I can say, yes, only trust them. Yes. And okay, so this is gates with the explanations, and in the end there are little exercises just to ask you to set up certain states for 1 qubit, for multiple qubits, yes, and to implement some schemes with a special, it's not hard what should be done there, yes, but still something just in order for you to practice, yes. And for those for whom it would be easy, there are more tricky things, like to implement certain 3 qubit gates. Yes, so like controlled swap. Yes, we know that swap is a 2 qubit operator, so we can do control to it. Just kind of please decompose it by yourself, or just okay, Grover algorithm we will do in the next class. So it's too early, yes, but okay, say I also wrote some scheme which is partially determined. Yes, so I didn't say to I didn't tell to all the poor states what is the result, but I showed to part of them what should be the result, and please fill up everything, the rest by yourself, in the way so that it would be easy for you to implement. Yes, so please, how to say, next time all questions are welcome. Yes, and now questions are welcome, of course. Yes.
I'm tempted to use Boolean on the CED. Would that be useful somehow?
What?
I'm tempted to use Boolean with the algebra on the CED.
On the CB?
Yeah, the next
6B. Yes, yes, yes. Of course, it's Boolean algebra. In fact, yes, yes, yes. You know, but please have implementation of quantum computer. Yes, of this scheme. Yes, but of course it's Boolean algebra. But you see, okay, I show only reorders here. Yeah, basically ask you to do most of them only reorders, except just this uploading thing. Yes, but please, how to say, find a way, you know, to do this. Yes, because I told the algorithm which should illustrate to you that okay, it is possible. Yes, but of course, in order to really do this, you need to practice a bit. Yes, so that's. But you see, with software development, it's always like this. Yes, I have say people tell you what is the, I don't know, for cycle, yes, while cycle, if operator, but unless you really do this, you not really understand it. Yeah, Wilson? More questions?
I'm still shaky on the fourth question.
Yes, so this is 2 qubits, yes. Then, okay, to any 2 qubit operator, there is a corresponding matrix. Yes, and all the matrices, both matrices which I showed here are unitary. So there should be a scheme which is based on C0 and, okay, on the gates which are available in, I would like to restrict not to C0 and 1 qubit, but to the gates which are available on the IBM. Yes, because for some of them there are some funny and tricky implementations. Yes, then in order to have this, yes.
So it's like just to be sure, we are filling all the blank spaces with zero.
Yes.
Okay. It's like we are passing the qubits in the matrix, and after passing it, the result should be the result of the product. Okay.
Yeah.
Okay. I'll try.
Yeah.
I'll try next lesson.
Yeah, you can send to me, yes, and the best way to send me something is the following. So you have here the text, yes, and I can then copy inside my one and to run it, to modify it, yes. This is the best way to send me, you know, answers, yes, whatever it is. So in text file, yes, basically. Yes. More questions? That's it, yeah? Okay. Thank you.